Hi there folks, we've not got much left of the normal distribution to do now, a couple of lessons and then we'll be there. We would have done the statistics course then and it'll just be on to mechanics for that side of things. It is important that you start uploading some work to me though, because I'm still waiting to see it, and the next stage will have to be phone calls home, so let's not push me to that folks, and let's get on with it. Right, well that's what we'll do. I've got myself my my Jaffa cakes from a little orangey burst of goodness, and even sparkling water. I've had that much tea and coffee. It's time to move on. Okay. Now here's our challenge for today: to use the normal distribution to approximate a binomial distribution. Well, why should I want to do that? To be honest, these days with the calculator, in many ways you don't sort of need to, but there are still many teachers out there getting the students to use the table. So this is in your formula booklet, your binomial cumulative distribution functions. See here, if you've got 5 trials, there's your n equals 5, and that keeps on going through to 10 there. And if I turn on, I get to 30, then I go on to page 33, and I've got this whole massive load of values here for all the different things that can happen if you've got 50 trials and your various probabilities there. If I turn on, ooh, we're on to something new. So that's as far as it goes. It'll only do 50 trials. Now in the calculator you can do more than 50, but we need to be able to do this as well. And it will be useful for other things too. But that's the main sort of point of it. So if we've got our binomial distribution, let's just remember what that looks like and what we're talking about. So you've got the first number inside there is our number of trials, and the second number is P for probability. And as I said, the formula booklet only goes up to n equals 50. Now, we can use the normal distribution to approximate if you've got a large, so we do it if it's appropriate to use the normal distribution if n is large, by which we mean bigger than 50. And this is important, but don't worry because they won't ask you to do it if it's not, and if P, the probability, is close to 0.5. You're probably going to ask me how close. Well, you'll get a sense of that once you've done a few of these problems. The other thing that we need to think about is our normal distribution. We normally have the mean, don't we, instead of a number of trials, and we have a probability. So in order instead of probability we have the variance, which is the what's that called again, standard deviation squared. So we need to be able to define these from there, and we can do that by saying the mean is going to be equal to the number of trials multiplied by the probability, and the standard deviation is going to be the square root of, now wait for this, the mean, which you get by doing the n times the p, and that's going to be multiplied by 1 minus the probability we're dealing with. Now you might be thinking, hang on, how the flip am I going to remember that amongst all the other things going on? So if you get your formula booklet and turn to page 8 and look at where it says discrete distributions, when you get into the exam you think, oh, that's to do with the binomial. Check on here to the binomial, and it tells you here that the variance is np times 1 minus p in brackets, and that the mean is n times p. And it gives you a way that you can do your binomial as well. So that's handy to have. So that can remind you how to get from the binomial to the normal. Right, so we'd better have an example. Here's our first example, so copy it down and see how far you can get before unpausing and letting me take you through it. So for part A, all it's talking about is our binomial model, as we were talking about just before. So we've got I think for x is going to be b. In the bracket, the number of trials is 100, and the probability that we get ahead is 0.53. So that's all that's asking for. Now, explain why x can be approximated with a normal distribution. Y is normal, mu, and standard deviation squared. Well, that's going to be 2 reasons. Because the number of trials is large, and that's all you have to say. You can then say that that's more than 50 if you like, but it's large, and probability is close to 0.5 or close to a half. Then finally, finding the values of the mean and the standard deviation. Well, the mean is easy, isn't it? The mean is n times p, so that's going to be 100 times 0.53, which is 53, and the standard deviation is that little bit trickier. It's going to be the square root of n times p, which we've just done, which is 53, times 1 take 0.53, which is the same thing as saying the square root of 53 times 0.47. And to 3 significant figures, that would be 4.99. Right, we've got 2 more examples to look at, but before we do, we need to think about the difference between the kind of data we've got when we've got a binomial distribution and a normal distribution. And the point of that is that a binomial distribution is discrete, whereas a normal distribution is continuous. Which means when we're looking at the binomial, we're only looking at whole number values, but normal distribution could go anywhere within it. And that means that if we are looking at a binomial distribution and we're approximating it with a normal one, we're going to have to do something to kind of standardize what's going on. Well, a little bit like, I think of this a bit like shoe sizes. So if you start measuring people's feet, people whose shoe sizes are size 6 are going to be lying anywhere within that a certain amount of centimeters or millimeters or whatever. They're not all going to be the same size. And then half sizes come in as well, but we don't want to get too confused by that. So if you're going for 7, you're between 6.5 and 7.5. So the point being made here, all this blue stuff is what we would need if we were going to estimate on a normal distribution bigger than 5. We'd have to be going bigger than 5.5, because everything, to keep the approximation sort of centered around the whole number is going to be 0.5 above or below. Now when we come to something like this, where it's bigger than 8.5 and less than 9.5, sorry, where we've got x is equal to 9 exactly, that's going to be a zone from 8.5 up to 9.5. And if we look down here, if we're going less than exactly 3, we've got to take in the whole of 3, so it's everything below 3.5. So if we're including the number, then that's going to be adding that bit more in, whereas if we're not including the number, it's going to be sort of taking that extra 0.5 away. Right, you're probably wondering what I was keeping hidden under here. Very exciting, it's our next example. So our binomial random variable, have a little look at it, pause the video, and then see how you've got on. So here they've already done the NP stuff. If you do 150 times 0.48, you get 72. And if you do the square root of NP times 1 minus P, you get 6.12. So they're saying use this approximation to find the probability that x is less than or equal to 70. So the first thing I would do is draw myself a little curve. So I've got 72 as my mean, and we want less than 70, so it's going to be something like that. So we know our probability is going to be less than a half, but less than or equal to 70 is going to include all of 70. So we actually are going to need to use the value 70.5 to take that into account. So then, if you get your calculator out, what we're going to be looking at is going into statistics mode, distribution, normal, cumulative. Our lower value has got to be 0, hasn't it? Oops, that's too soon. Our upper value is 70.5. Our standard deviation is 6.12. The mean is 72. And that's giving us a probability of 0.40319. So remember, always want these given to 4 decimal places. So the probability is going to be 0.4032. Right. So the next. Right, folks. Sorry about this low-tech solution here, but I just did a perfectly good demonstration that the computer decided to say no to. So what we're doing here, when you're sketching a curve, something I didn't do last time, if you put your bell curve in before you then pick where you want to call your mean, then it tends to look a bit better. So we've got 72 there. We're going between 80 and 90, so I'm just going to start by writing 80 and 90. Some of you are probably thinking, but we don't want exactly 80 and 90. And you're right, we don't want exactly 80 and 90. We want to include 80, which means we need to go a bit bigger there. So we need to go down to 79.5. But we don't want to include 90. So we need to take that down to 89.5 so that we don't include that bit in there as well. And then that's what we're going to be popping into the calculator. So I put 79.5 as my lower, 89.5 as my upper, keep everything else the same, and that gives us a probability equal to 0.1081 to 4 dp, which is what they like to see. Okay. And on to our last example for the day. A little bit different, this one, but have a think about it and see what you can come up with before you let the video run and me explain it to you. Right, so in order to work out the percentage error when using a normal approximation, we need to know what it actually is for the binomial approximation. This is the reason why they've gone for exactly 50 yellow flowers, because if you were using the formula booklet as you're allowed to in the exam rather than the calculator, that's the biggest value that you could have on that. So the first thing we're going to do is work out the binomial, the actual binomial value. So we're going to be going with 50 trials and a probability of 0.55. We're going to be putting that in the binomial cumulative, and we want we want exactly 50, don't we? So a lower of 50, an upper of 50, hang on, sorry, we've got a sample of 80 flowers. So I've talked nonsense there, haven't I? I needed to be putting 80 in there. We want 50, so it is more than you'd be able to use. So you do need to use a calculator on this anyway. So then we'd have the number of trials is 80, the probability 0.55, and that gives us 0.0365 to 4 decimal places, which is all we need. So hang on, I should have written probability x equals 50 equals 0.0365, shouldn't I? Right, so then we need to go through the normal distribution process to find out what that would be. So for normal, we need to know what that is, don't we? That's going to be, remember, NP, isn't it? And then this is going to be the square root of NP multiplied by 1 take the probability. So NP will be 80 times 0.55, which is 44. And then if I do the square root of 44, 1 minus 0.55 is 0.45. If I do that, then I get 4.4497. That'll be squared, won't it? And then we need to be thinking, when we have 50, let's just do a little drawing. So we're looking at 44, and we want the probability of 50. But I'm going to put a narrow strip in here, because to get 50 we're going to need the zone between 49.5 on the normal distribution on the continuous scale to 50.5. So then if we go back to normal, we want the lower, not of 50, but 49.5 up to 50.5, and everything, and we've got 4.4497 for our standard deviation and 44 for our mean, and that's giving us something very close to what we got on the binomial, which is encouraging. To 4 decimal places is 362, and the question is asking us what is the percentage error. So the error is going to be 0.0365, take the difference between them basically, which is 0.0003. And as a percentage, the percentage error is going to be that out of the actual accurate amount, which is the binomial one, and then to turn it into a percentage we multiply by 100, and if you do that you should get 0.82. So it's 0.82 of a percent error. So not very much, less than a 1% error, and depending on what it is you're talking about, that may or may not be significant. I don't think it's very significant here. Right, so that is all those examples done. I'd like you to have a little go at page 55, exercise 3F. Question 2 will sort of help hone and practice the skills a bit before having a go at some exam style questions 7, 8 and 9. And do make sure you upload your stuff back to me to let me know how you got on with all of that. All right, folks, cheerio.